In this lecture, we're going to talk about empirical and molecular formulas. So we'll cover two examples here, and then, of course, you have plenty of example problems in your work packet. Okay, empirical formula. We're dealing with the smallest whole number ratio. Okay, from element to element. What elements are involved, and what would be if you were to reduce them or simplify them? What would you get? Your example here is hydrogen peroxide. Okay, simplifying that, we have a 2 to 2 that can both be divided by 2's. So that would be a 1-to-1 ratio. Okay, that would be simply put water, H2O. Well, you can't simplify it anymore. So water's empirical formula is H2O. So empirical is the simplest. Okay, if you can reduce it, you have to do it. Okay, so how do we calculate empirical formula, or how do we figure out what an empirical formula is if we don't have it? Well, in this case, we are able to take a sample of caffeine. Okay, and we were able to determine that there's 49.5% carbon, 28.9% nitrogen, 16.5% oxygen, and 5.1% hydrogen by mass. We're able to figure out by their mass. And there's different techniques we use in chemistry to determine that. From that, we want to figure out, well, what's the actual, what's the empirical formula? What's the simplest ratio of carbon to nitrogen to oxygen to hydrogen? Okay, and so that's what we're going to do now. We're going to calculate that. So here's how you set it up. Well, let me say this. You'll see that we have grams here. Well, where did those grams come from? We were in percents. When you're given percentages, percent means per 100. So did they tell you how much that sample was? They didn't. Okay, so when they say, generically speaking, you have a sample and you have this many percentages, you get to assume, okay, well, my size sample is, I would always say 100. If I said 100 grams, well, these percents then say, well, it's 49.5 per 100. Well, I have 100. So that means I can directly translate this, transfer it from percents to grams. And that's what we did. We made that assumption. If they were to give you something and they said a sample of caffeine was found to have 49.5 grams and 28.9 grams, well, then you just use the numbers you have to convert from grams to moles. Okay, that's what we want to do. We want to convert from grams to moles here. So in this case, 1 mole, 1 mole, 1 mole, 1 mole, and we put up the value from the periodic table because your periodic table was written based on 1 mole of that substance. Okay, so 12.01 for carbon, 1.01 for hydrogen, 14.01 for nitrogen, and 16.00 for oxygen. 49.5, we divide by the bottom and multiply the top. 49.5 times 1 divided by 12.01, 4.12. Notice the sig figs matching up. 5.1 grams, okay? Grams of hydrogen, can't tell you that's moles of hydrogen. Good, because that's where I wanted it to be. Now we do 28.9 divided by 14.01, 16.5 divided by 16.00. Now we look over here and we can see 4.12, 5 moles, 2.06, 1.03. What you're looking for now, let me do a cheat there, okay? What you're looking for, you see these numbers? You're trying to find the smallest one, okay? Which one produced the smallest number of moles? Well, you notice here that these numbers weren't round numbers, right? Okay? What you're going to start looking at this and say is, I want to divide this by the smallest number here. What's the smallest? You have 4.12 versus 5. 4.12 is smaller. 4.12 versus 2.06. 2.06 is smaller. Now 2.06 versus 1.03, that's your smallest number. You're going to divide all these numbers by 1.03 moles. 1.03 moles. 1.03 moles. Again, you're leaving it generically just moles. You don't want to say moles of oxygen. Well, that complicates your units then. Because what's going to happen then is 4.12 divided by 1.03, that equals 4. Moles divided by moles, that's left out. I'm left with 4 carbons. And over here, when I divide that, I'm going to get basically some number close to 5. When I say some number close to 5, I'm talking about like 4.9 something, 5.03. If you get like 4.5, that's a problem. You can't just round that up. But that would be a sign to tell you that you need to multiply all of it by 2, 3, or 4 to where you can get very close to all whole numbers. Okay, so we'll continue on, and you can see on your next slide, you divide this, you got 4, you divide this, you got 2, this divided by itself is 1, this divided by this, basically 5. Okay, so this tells you this number, if it's a whole number, you're going to bring it down here. So we put carbon, hydrogen, nitrogen, oxygen. Okay, and so we have 4 for the subscript. This number here is your subscript. 5 hydrogens, 2 nitrogens, 1 oxygen. Okay, and that's the empirical formula for caffeine. Okay, so now that we have that, again, if you were to have something like this, if it would have been 4.5, okay, you can't have half a carbon. That's a problem. So what you'd say is, well, I have a whole number here, a whole number here, a whole number here, and I got this half. Well, what should I multiply by? 2, 3, or 4? Well, I'd multiply this by 2, and you have to do it to all of them. Times 2 would say there's 9, and this one times 2 equals 10, times 2 equals 2, times 2 equals 4. And so then I'd say my actual empirical formula, the simplest, would have been C9, H10, nitrogen, 4, O2. That's what I would have said. Okay? And that's what you go with. Since that's not the case, we'll disregard all that, but realize that may come up in some of your example problems, and that's how you handle it. So that's your empirical formula. Molecular formula. This is the real deal. Okay? Empirical, you simplified it. Molecular, what is it truly? What elements are there, and how many atoms of each? Okay? So that's what we're looking at. The empirical formula for hydrogen peroxide is H2O2, because there are literally 2 hydrogens and there are literally 2 oxygens. Okay? So this is what's there in reality. You can find the molecular formula if you have the empirical formula. Okay? So we know the empirical formula for caffeine is C4H5N2O. That's what we calculated. So what we do need, and you'll always be provided this, is what's the molar mass of the caffeine? Okay? They'll give you this number. This number goes on top. You always do the molar mass of the actual molecular formula on top divided by the empirical formula mass. Well, they didn't give me the mass, but can you calculate it? You can. You'll have 4 carbons, 5 hydrogens, 2 nitrogens, 1 oxygen. Okay? So we're going to put that over here, and we'll do 194.2 divided by 4 carbons, 5 hydrogens, 2 nitrogens, 1 oxygen. And when you calculate this, you should get a number around, what, 80, actually probably about 95-ish, somewhere in that ballpark, actually 97. Somewhere in that ballpark would go down here. You do 194.2 divided by the sum of all of this and your product, and you'll get 2. Well, what do you do with this 2? You take this 2 and you multiply every single subscript, including the one that wasn't represented here. So this goes 2 times 4 is 8, 2 times 5 is 10, 2 times 2 is 4, 2 times 1 is 2. 8, 10, 4, 2. Excuse me. And that's your molecular formula for caffeine. There are literally 8 carbons there. There are literally 10 hydrogens, 4 nitrogens, and 2 oxygens. That's a molecular formula. Okay, how can I complicate that? Or how can it, don't blame me. How can that be complicated for you to make it a little bit higher? Well, we can start you out from empirical formula and just make it, I could just give you, we have this, we have a sample of caffeine, and it's made up of this percent of this by mass. Find its molecular formula. That means you have to go all the way through empirical formula and end in molecular formula, just all in one big problem. We wouldn't break it up and ask multiple questions. Although we could ask multiple questions, okay? And that'd be like a waterfall question that we do in the written section, okay? But we would just make it all one question, multi-step. But other than that, I want you guys to really digest this, okay? If you don't get it, watch again, come talk to me. We're about to go into combustion analysis after this. You really want to have digested this material, because if you can't do this, you can't do combustion analysis, okay? So ask me questions if you need to. Otherwise, carry on. See you soon.